Okay, you're live.
Okay. Hi, everybody. Welcome to another episode of SETI Live, brought to you from the SETI Institute, appropriately enough. My name is Seth Shostak, and I'm an astronomer. I'm the senior astronomer, actually, because I think I'm older than any of the others here at the SETI Institute. And today we're going to talk with a special guest, but aren't all the guests special? We're going to talk with a special guest about a new scheme to find ET. Now, I doubt that many of you have any qualms about the idea that there might be an ET to find. We're going to not even touch that subject. We're just going to talk about how to do it. And my guest is Sofia Sheikh. She's there looking at you from an apartment in San Francisco. Sofia is, in fact, let's go wave to the crowds. All right. Sofia is a PhD candidate in astronomy and astrobiology at Penn State University, which is located in lovely State College, Pennsylvania, somewhere in the mountains of the East Coast. And she's planning to do an experiment that might, in fact, turn up proof that we have some cosmic company. Now, before getting onto that, let's get into this way, Sofia. One of the problems with SETI, as it has always been done, or almost always, is that you use big antennas, you point them in the direction of some nearby star systems, hoping it has a planet where there are some, Klingons or whatever camped out, and listen for signals. However, typically you only listen for a few minutes at any given frequency, just a few minutes. Now, when you think about that, a few minutes compared to the age of the universe, right? How many minutes has it been since the Big Bang? Well, it's on the order of like 5,000 trillion minutes. And you're giving ET only a 2-minute chance to get in touch, not to mention the fact that you might be pointing in the wrong direction. So, Sofia, is there a better way?
There are many better ways. And the question is, which one is the right way? And we don't know the answer to that yet. But I like to use the analogy of trying to find someone in a city, but you don't know where you're going to find them or when you're supposed to meet them. And if I just told you, if I dropped you in New York City and said, you have to find someone like in the next 24 hours, go, they're going to be looking for you as well. You might try something like, okay, maybe I'll go to Grand Central Station or Central Park, or when would I meet them? Well, maybe noon, midnight. Like there's some special places and special times that are well known and you might think are better choices than others. And we try to apply that same logic to space to say, what special places and special times should we look if we want the best chance of finding alien life?
They have to be special, not only for us, but special for ET. And this has to happen without any email traffic back and forth with ET.
Right. And that makes it a bit trickier. So we have to rely on things that we know that we can see from Earth. And we also know that ET would know about and could see from wherever they are. So one way of doing this is something that I've been researching for a couple years now, which is looking within the Earth transit zone. So that's I call it ETZ for short. And the ETZ is the special region of the sky. And it's kind of hard to explain without a model, but bear with me. If you were to be in the ETZ, pretend you're an alien on a planet in the ETZ, and you look with your telescope at the solar system to Earth, where we are, you would see once a year the Earth crossing over the face of the sun and blotting out some of the sunlight. And so because you're in that special part of the sky where the Earth and the sun are lined up, you would know that Earth is there. You could detect Earth as a planet. And so we think that might be one of these special places that we could look that might be more likely to have an alien signal, because the aliens might know that we're here.
Okay, so to summarize this, I think many of the viewers here may be aware of the transit scheme for finding planets around other stars. I mean, you don't actually see the planet, but you look at the star and you just measure its brightness. And every now and again, every so many days, the brightness gets dimmer, and then it gets bright again. maybe one part in 10,000 or something. And that's how you know the planet is there. But if you see that it's doing that for example, 365 days, just to pick a random number, you would say, okay, we know that there's, some planet there more or less the size of the Earth. And so they send a signal, since they're better astronomers than we are, and they know the distance to our solar system very accurately. They send a signal to arrive just as we're crossing in front of the sun, seen from their point of view, right? So
Exactly.
So now we know, okay, if we look away from the sun, we're looking at them.
Yeah, and that's the time aspect. So in the past, like I have looked at some stars in this ETZ region, and I didn't find anything, but I only looked at 20 stars. And each one I only looked at for a total of 15 minutes. And like you said, 15 minutes is not a lot. Their transmitter just could have been off for a little bit. Maybe a wire broke or something. I don't know.
Summer vacation.
Exactly. Telescope's closed. But if we have a special time, then that saves them power too. They're like, oh, okay, every 365 days we'll send a signal. And then they can kind of reserve all their power and only use it for that short period of time. So that's great for them. And it's also great for us because, like you said, we know when to point our telescope in their direction, which is to say, look opposite the sun. And if you see anything signaling us from opposite the sun, well, that's going to be an interesting time and place.
Okay, so unlike SETI in general, where you just point at nearby stars, most of them probably do have planets, but you don't know much about those planets, even if you know there are planets. Instead of doing that and hoping that they're beaming a signal at you, all the time because it's a high school science fair project for some kid who's got access to a 1,000 trillion watt transmitter, or maybe less if he has a big antenna, and beaming something to Earth, but that for what reason I don't know. This one they could just do it, once a year. They could just send a ping in our direction, and an experiment that was always looking in the direction opposite the sun would find it, right?
Exactly.
Okay, this seems like a decent idea because it tells you where to look and when. Well, has anybody done it? I mean, why hasn't anybody done it?
Logistics, which is often the answer for SETI projects. If you want to do this and you want to cover the entire Earth transit zone, you need to be constantly looking at that point opposite the sun. But Earth rotates, right? So as you're trying to look at this point, it's moving across the sky, and eventually the sun is going to rise from wherever your telescope is, and you won't be able to see the anti-solar point anymore. So if you really want good coverage, you need telescopes on like both sides of the Earth, so you can be constantly monitoring. And if you want to look at the whole Earth transit zone, it'll take you a whole year of observations because you need to look at each individual section at this special time. So getting a hold of a telescope to do half of the Earth transit zone or 2 telescopes to do the whole thing for a whole year is pretty tricky.
Yeah, tricky, almost impossible, but not quite. I mean, if you wanted to use, the famous radio telescopes of the world, the Arecibo telescope down in Puerto Rico, or the FAST telescope in China, or for that matter, even the Very Large Array in New Mexico, which is going to be used for SETI experiments. I mean, they're not going to give you a year's worth of time to do this every day, right? That's just, you're fighting all the radio astronomers because they want time on the telescope, and they'll send some guys from Chicago with narrow ties and fedoras and make sure you don't do it.
Yeah, I had to give you an idea, write an entire multiple pages long proposal for a different project I'm doing right now to get 10 hours of time on the Green Bank telescope in West Virginia. So even to get kind of hours of time, you have to be competing against all these other projects and ideas, and it's a pretty hard sell to convince someone to give you a telescope for a bit of time every night for an entire year.
All right. Well, as they say in Chevy's household, let's cut to the chase for a moment. And, you have plans to do this, but you have a telescope in mind as well.
I do. because of these kind of logistical constraints, I need a telescope that I can commission for, say, half an hour every night for a year. And that's tricky. But it just so happens that the SETI Institute has an instrument that fits the bill, the Allen Telescope Array. So I'm currently working on a proposal to use the Allen Telescope Array to perform this kind of anti-solar point search.
For those of you who don't know the Allen Telescope Array, allow me to point it out. Notice how my hands disappear. This is a medical condition. That's the Allen Telescope Array, and I'm not actually sitting in front of it, although you probably couldn't have guessed that. It's located about 300 miles north of where Sofia is sitting, north of San Francisco in the Cascade Mountains, and it indeed is the property and now actually the responsibility of the SETI Institute running that array. And because it is the SETI Institute's telescope, we don't have to compete with people who are studying other astronomical problems for time, right? So that'll do. Let me just, Sofia, tell you where people are watching from. We have the UK. You probably heard of the UK. Poland, London. London is, this is probably London, Ontario. Kansas, India, Australia, K-Pax. Ha! Oh, I think that was that a Bruce Willis film? I'm trying to remember. It was Florida, Cornwall. Gee, these UK people are not happy to say UK. Virginia Beach, Salt Lake City, Virginia Beach, my own stomping grounds. Michigan, Italy, Cloverdale, Indiana, Venus. See, that stuff in the atmosphere, it is alive. Buffalo, Mexico, Moldova. No, Moldova. All right, sorry, Moldova. I'll get it right. New Zealand, California, Brazil, Berlin, Iowa. Well, that's just the start. Those were the first 20 people to come into the room. All right, so going to use the Allen Telescope Array, spend a year. That will actually give you sort of half the coverage you want because of the unfortunate circumstance that the Earth rotates. And when the sun is up, it's hard to look in the anti-sun direction unless you're maybe a mole or something and can tunnel through to the other side. Okay, well, you could take a second year and do the other half, right?
Yeah, absolutely. It would be great if we had an Allen Telescope Array 2 that was exactly on the other side of the Earth. Pesky Earth is rotating all the time. But within 2 years, then you could cover the entire Earth transit zone at the anti-solar point, which would be very exciting and no one's ever done.
So what we really do need is, in fact, yes, I guess just 180 degrees in longitude would do it. It doesn't have to be the antipodes of California. Okay, well, maybe somebody will fund building one of those sorts of things. Now, when you do an experiment like this, you have to make choices, not only about where to point and when and so forth, but things like, well, where should you tune on the dial? What frequency should you observe? What's the plan there?
The short answer is that we're still working it out. The Allen Telescope Array has a pretty wide range of frequencies that we could record from, I think, about 1 to 12 gigahertz. And a lot of searches in the past have been kind of between 1 and 2 gigahertz. There are some cool astronomical lines there that we think, if we think they're cool, maybe aliens also think they're cool. But the short answer is we don't really know where we should expect a signal to come in. So we want to look at as much of the range as we can. So we haven't decided exactly which frequencies we're going to use out of that range, but we're going to try and use as much of it as possible and record as much as possible so we don't have to make assumptions about exactly what frequency they're going to be transmitting at.
But again, I mean, this whole idea is predicated on trying to second guess ET, right? And try to figure out, okay, I mean, if ET wants their signal to be found, if they take the time, the trouble once a year to send a message our way, like, are you interested in a magazine subscription or whatever message they have for us? If they're going to do that, then they probably would pick a frequency that they think we could guess, right? And so maybe those are the frequencies you've already talked about.
Yeah. So there is a particular line called the hydrogen line, which comes from basically everywhere in space. Hydrogen gas emits at this frequency. And so that's been the subject of a lot of SETI searches in the past. But maybe, that's pretty crowded. There's a lot of, hydrogen gas emitting there. So maybe you take that and multiply by 2 or multiply by pi or something else like that. Or, fingers crossed, maybe they'd make it easy for us and emit at a bunch of frequencies at once, spaced apart by some special number or something.
You'd think they'd make it easy for us, after all. I mean, if they want us to pick up the message, I would think they would do everything they could to make it easy, even if it costs them more, money, whatever money they have. Now, Sofia, you're not doing this project alone, as I understand it. You have a couple of people involved. But one of the people you have involved is actually a high school student by name of Saul. Can you tell us a little bit about Saul? I mean, it's not normally the case that such experiments involve high school students.
Yeah. So this past summer, I was involved in a project called Intro to Astronomy. And it's a free online course that is actually directed at university students, so freshmen or sophomores who think they might want to be an astronomer and go into astronomy as a research career, but they've never done research before and they're not sure how to get involved. And so an astronomer at UC Berkeley, Howard Isaacson, put together this online virtual class over the summer where anyone around the world can sign up and go through this course about how do we take data? How do we analyze data? Learning to code, learning to present scientific research. And while we recommend that it's for freshmen and sophomore college students, we have a lot of participation from high school students as well, who are just super interested in astronomy. And Saul was one of our students for Introduction to Astronomy this past summer. And for his final project, he said, hey, I heard about this Earth transit zone idea, and there's this anti-solar point thing. Could I do my final project on that? And I was like, this is so cool. So I worked with him for his final project over the summer, and now he's involved with kind of helping me write the proposal, and it's been really fun to work with him. And
he seems very competent. I mean, you don't expect too much from a high school student. Maybe I'm wrong. When I was in high school, I expected more, but you don't. But he seems quite competent, right? I mean, this is not just your average high school student.
Absolutely, and it's he actually found the program, I believe, by emailing a professor at a university and saying hey, I'm applying to college soon. Do you know any way I could get research experience? And the professor recommended this program, and then I was a mentor for the program this summer. So that's how it all came together.
Okay, Sophia, we're going to go to questions eventually here, and eventually it's not going to be too many minutes from now. So for those of you out there who might be watching this, and we've added quite a number of countries, including Iowa, which is a really interesting country, write your questions. Sophia will take them on. I do want to ask you another question. If I tell people that we do SETI at the Institute, it's not a big surprise to them given the name of the organization. And they'll say, well, have you found anything? And, I have to admit, no, we haven't found anything yet. And that's true for all SETI experiments, not just the ones being run here. What do you tell people when they say, well, why not? Maybe there's nobody out there. Maybe you're wasting your time, or maybe radio is just too old-fashioned or something like that. What do you tell people?
So my response to that is that we have barely started searching, so we can't really say we haven't found anything yet. And then usually the response is wait, but I've been reading news articles for 60 years about this. And it's always, we haven't found anything, we haven't found anything. And the analogy I like to use is imagine you're looking for life in Earth's oceans. So all of Earth's oceans all together, you're trying to find a fish or something like that. If we pretend that that's all of space, how much have we searched in SETI? And the answer is, depending on who you ask, about a bathtub's worth of water, maybe a hot tub, maybe a small swimming pool by now. But if you just go to the ocean and scoop up a bathtub and you don't see a fish in it, you wouldn't say, well, gosh, why are there no fish in the ocean? So the answer really is just that we haven't really searched a lot. And that example is only for radio wavelengths, not even thinking of all these other ways, which we totally should be doing at the same time, right?
Well, tell us a little bit, briefly, what other ways could we be looking?
So one kind of complementary way is like, okay, maybe they're sending radio waves, or maybe they're sending signals in optical wavelengths. Optical's a little tricky though, because of course stars emit optical wavelengths. That's how it's bright in the daytime. Our sun is shining a bunch of optical light everywhere all the time. So if you're looking for artificial alien signals in optical wavelengths, they need to have something special to distinguish them from their stars. So there are a couple different techniques people use, but one of them is looking for lasers, because you can't outshine a star with a flashlight, but if you pick one very specific frequency and shine a laser at that frequency, then we would see like, oh, the star is normal, 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 really green, normal, normal, normal. And that spike, say, in the green might be something that we could detect.
Okay, so by putting all the energy into a narrow range of wavelengths, at one color, you can outshine your star, which is going to be making it difficult for anybody to find you. It's like you can use a laser pointer to outshine the sun. If you get up to somebody and aim the laser pointer in your eye, don't try this at home, but so that's the idea. Now, there are experiments to look for flashing laser lights, right?
Yeah, there have been a couple over the last, I think, 20 or 30 years mostly. Nothing yet, but I think it's an area that kind of hasn't had as much development as the radio searches, and those are continuing to expand as well. And so they're kind of happening in parallel.
Okay, now, Sophia, one last question. We'll go to the questions from the audience. But are you optimistic? I mean, getting involved in SETI, you've got many years of career to look forward to here. And you could be studying, the line broadening mechanisms of forbidden transitions and, stars or something, really interesting like that. Or you could be doing SETI. It takes a certain kind of mindset, a certain sort of personal philosophy, does it not, to do SETI, where you might not find anything in your lifetime?
Yeah. So I think the thing I like about SETI is I'm looking for aliens. That's just cool. But also B, it allows me to be pretty creative. Thinking about like, what would we think that the aliens would think that we would think that, and I really like getting to kind of employ that kind of creativity in my work. And there's just so much that we haven't done yet. Kind of like I was saying, we've only searched this bathtub of water out of oceans worth. That there are so many cool strategies like this anti-solar point search that have just never been tried. And so I think there's so much low-hanging fruit, so many really cool projects that just need someone to come along and do them. And that makes it really exciting for me.
Great. All right, Sophia, we're going to go to some of these questions, the ones that have made it past Rebecca, who is our filter. She insists that all questions be timely and in good taste and so forth. Let's see. Well, actually, this first one is kind of interesting in a way. What if all the aliens died? Is SETI looking for signs of fallen civilizations? I mean, it could be, they become technological and then they blow themselves up, or something else that might ruin their whole days. So what do you say to that? Anything?
Some people have thought about it, but it's not something that's been done a lot because, well, not much in SETI has been done a lot. There is a really cool paper that talks about, like, say we had a neighbor civilization that discovered nuclear weapons and blew themselves up. What would that look like to us? Could we see that happening on another planet, around another star? Or what if they created a bunch of nanobots that ate everything on their planet and turned the whole planet into paper clips or something? Could we see that? So there are some people who have thought about the theory of what these things would look like. But as far as I know, there aren't really any dedicated searches to look for those signals, because it turns out they're kind of hard to see. Dead civilizations are not as bright.
Well, I think by definition, If they're dead, they're clearly not as bright. Yeah, it's very hard. Actually, people have considered, I did this quite a while ago, but there were suggestions that maybe the way to signal the aliens, in case you want to do that, is to, let loose some of these surplus nuclear weapons. Have a rocket carry them into space and blow them up so it doesn't, mess up your own existence, and the aliens will see that. But it turns out, even an H bomb going off in space is not very bright. And besides, you have to confront the possibility that something goes wrong with the rocket on the way up and you take out Trenton, New Jersey or something. So that would be unfortunate. But okay, let's go to another question here. Well, can you use space-based telescope for this kind of work? Space-based telescopes.
Yeah, so depends what you're doing. If you're doing something, say, looking for these kind of transit dips, but maybe weird transit dips, and you're looking for aliens that way, there are telescopes like Kepler and now TESS that are looking for planets and could maybe find aliens doing weird things to their planets. So those are space-based telescopes that can be used for SETI work. As far as what we've been talking about mostly today, which is radio waves, that's mostly on the ground. And honestly, that's for convenience, because radio waves go straight through the Earth's atmosphere. They don't get blocked by even some amount of clouds or oxygen or everything that's in the atmosphere. So you can easily observe them from the ground, and it's a lot cheaper to use telescopes on the ground than telescopes in space. So for the most part, the work that I do is with ground-based radio telescopes.
All right. Let's try now. Everybody got that, I'm pretty sure. It's also the case that you want bigger is better when it comes to, well, almost any kind of telescope, but certainly radio telescopes. And it might be tough to put a 500 meter diameter antenna into space. That would, you'd have to be able to fold it up and get it into a rocket. I don't know that's so easy. Okay. How much data could an alien message contain for, say, a steady year of transmission to Earth in optical as compared to radio signal? If they were transmitting it, could we download the Encyclopedia Galactica in a month, a year, a decade, a human lifetime, maybe longer than that?
That is a good question. It depends a lot on how, kind of what you're assuming, because if you're just sending one frequency, you're kind of limited to, moving it around or making it brighter and quieter to transmit information. But say if you have a comb of them, they're transmitting at 100 frequencies at once, then you can get 100 times more data across. So it does depend on the specifics. As far as radio versus optical, the short answer is either one is a lot better than trying to send some individual bits through turning your star off and on or something like that. Electromagnetic communication is what we use on Earth, and we use both radio for things like GPS and cell phone communications and things, but we also use fiber optics, so optical wavelengths, to send information. So I'm sure there's more specific information on exactly in which scenarios you want to use radio versus optical to get more bits across. But it really kind of depends on the specifics.
Yeah, well, it certainly depends on the power. Actually, I have to say, I did some calculations on this once. And it turns out if you went to optical, if you used a laser, you could, even at one frequency, you could send the Library of Congress in 2 days or something like that. If you want the aliens to have access to the Library of Congress. Of course, that's also... do our TV and radio signals have a chance of being detected by extraterrestrials?
Depends how big their telescopes are. So we have been sending out radio and TV signals for almost 100 years now. And even though we direct those signals, of course, to towers on the Earth, some of it leaks away. But we're not intentionally broadcasting our radio out to space. So anything that gets out is kind of quiet because it wasn't meant to go beyond the Earth. But it does just go and keep going at the speed of light. So for example, something that's 50 light years away would be getting transmissions from Earth that were broadcast in about 1970. The problem is because they weren't really meant for alien ears, they're very, very quiet. So you would need like huge telescopes to be able to pick up on these signals that we're sending out. If they wanted to, they could do that. But it's a lot easier to see things like radar or something like that, where we're sending brighter transmissions out to space for purposes other than Earth surface entertainment.
Well, I mean, that brings up the obvious question. If the aliens, for example, were, I don't know, just name something, 50 light years away. That's pretty close, actually. If they were 50 light years away and they had a SETI experiment like the ones we have, would they be able to pick up, television from our planet, or even radar for that matter? Would their experiment be sensitive enough to do that at a distance of 50 light years?
In general, no. I think is the answer here. I usually think of like leakage signals like this, TV or radio, would really only be detectable to another Earth-like planet within like a couple light years, maybe 10 light years if you build a really big telescope. But once you get out to 50, that's starting to get, our radar can reach that. We would be able to detect our own radar there, but TV and radio, not so much.
The question is whether watching radar is as interesting as watching reality television. And I think the jury's out on that. Okay, I'm going to go for one last question here. And we'll let you go. One day, we don't have any names here, so I don't know who said this, but they'll know themselves. One day, will SETI or NASA place a radio telescope on the moon? And would that be of advantage in looking for ET?
I would love a radio telescope on the moon. Specifically, I would love a radio telescope on the far side of the moon, where the Earth is hidden, so we don't get all of our TV and radio leaking in. And the great thing about the moon is, at least right now, we don't have satellites and planes and GPS and cell phones and Wi-Fi sending all of their signals up. Because a lot of what we do with SETI is look for signals that aren't produced by space, but could be produced by technology. And when we do that, we find a bunch of signals produced by technology, human technology. So as far as how it would affect astrobiology, SETI research would be a lot easier. We'd be able to look at certain frequencies that are really hard to see from the surface, because that's where, say, cell phones transmit at. So I have my fingers crossed. There have been some proposals for this, but nothing in the works yet.
I think it's a matter of money, isn't it? I mean, to put a telescope on the backside of the moon, I mean, to begin with, you'd have to put a restaurant there, I would assume, because the cuisine that's offered there is rather limited so far. All right. Well, listen, Sofia Sheikh, I want to thank you so much. Sofia is, again, a PhD candidate in astronomy, astrophysics, and astrobiology at Penn State University. That's in a part of Pennsylvania that, the major candidates are not visiting for some reason. But in any case, and she's going to be using the Allen Telescope Array back there to look for ET in a new way that might, this might be the one that pays off, in which case, Sofia, you can just sort of sit back, file your nails as you fly to Stockholm and collect your prize. So I'll be looking to that. And I, by the way, want to tell all the viewers here the usual stuff, but this is important. Be sure to check out the website of the SETI Institute at SETI.org, and you'll find, all sorts of information there about our work, not just in SETI, but also astrobiology. You can sign up for our newsletter. You can follow us on Facebook, Instagram, Twitter. You can do all that stuff and learn more about SETI than, your relatives ever thought you should. So please do that. Sofia, thanks so very much again. I'm Seth Shostak, and we'll see you next time on SETI Live.